Hi, this is John Whitaker for the Probability 1 class, and this is video lecture number 3. And so we left off last time about conditional probability and a fact related to it. And in particular, what we had was the probability of A intersect B, where A and B are two events, is equal to the probability of A given B times the probability of B. And we did an example of that last time. What I want to do is this rule can be extended, and here's a fact. A lot of people call it the multiplication rule, but here's what it says. It says the probability of E1 intersect E2 intersect E3 intersect, and keep going up to intersection of En is equal to the probability of E1 times the probability of E2 given E1 times the probability of E3 given E1 intersect E2, so E1 and E2, times, and finally I'll say the probability times the probability, let's see if we can get this in, of En given E1 intersect all the way up to intersecting En minus 1. En minus 1. I hope that's visible. And let's look at proof of this first. So here, note that if you look at the probability of E1 times the probability of E2 given E1 times the probability of E3 given E1 intersect E2 times the probability on up to the probability of En given E1 intersect all the way up to En sub 1, event N sub 1. If you look at that, that's the same thing as the probability of E1 times, this conditional probability is the probability of E2 intersect E1 or E1 intersect E2 over the probability of E1 times, again this is the probability of E1 intersect E2 intersect E3 over the probability of E1 intersect E2 times, we'll keep on going so we get to the probability of En or E1 intersect E2 intersect all the way up to En over the probability of E1 intersect E2 intersect all the way up to the intersection up to E sub N minus 1. And if you look, what you see is that the probability of E1 will cancel with the probability of E1 in the denominator here. The probability of E1 intersect E2 cancels out the probability of E1 intersect E2 here. And this will continue throughout, and what we're left with, these cancellations will continue, and what we're left with is simply the probability of E1 intersect E2 intersect all the way up to En. And I'd like to do an example of that, where we'll use this very simple example. So let's say an urn has 8 white balls and 3 red balls. let's say 3 balls are chosen one after another without replacement. Someone might ask, find the probability first ball is red, comma really indicates and. Second ball is white, and then comma, the third ball is white. That's our problem. Okay, so the way that I can do this is I'll say, well, this is equal to. All right, so I'll say it's the probability by this previous fact that the first, well, let me start again just for a second. So that was our direction, our command, find this. So here, I'll say, note, the probability of red, white, white will be equal to, well, it's the probability of first red, so that's the E1, and these commas indicate and. So first is red, second is white, third is white, times the probability by the previous fact that the second drawing is white, given first is red, and then that will be multiplied by times the probability that the third is white, given the first is red and second, that's intersection, second is white. Second is white. So that's what we're looking at. And so filling in numerical values for what we have. The probability that the first ball was red, well, there were 3 red balls, so it's 3 out of the 11 balls that are there. And really, you'd multiply that by, okay, how many ways could you get a ball that follows? 10 out of how many balls you could pick there. And then the next ball, we don't care what it is per second, so that's going to be 9. Okay, so really, these two combine just to be 1, but that's what we have involved in the calculation that the first ball is red. But since these two guys are 1, I'm just going to exclude them. So this is the probability that the first ball was red. The probability that the second ball is white, given that the first ball is red, that's a conditional probability, and one that's easy to calculate by putting ourselves in that position. So the first ball is red, so that means there are 2 red balls and 8 white. So what's the chance that we get a white ball? It's 8 out of 10. And now, given that we have a red ball on the first draw and a white ball on the second, that means that our urn, as we pick the third ball, consists of 7 white balls and 2 red balls. So we got 9 balls from which we can choose, and the number of white ones there are 7. And so that's the answer for this problem. Now I want to indicate when, or some wording that indicates a conditional probability. Is, let's just comment here, is the percentage of A that is B means the probability of B given A. So it's that conditional probability. Okay. That's something to keep in mind when you're reading a problem, that phrase, in terms of what it's indicating. Now, in this problem we just worked, one of the things that came into play with discern was that it's easy to compute, a lot of times, a conditional probability when you're asked what happens next, given what happened in the past. And I had said in the previous lecture that it's a little bit more difficult to compute the conditional probability when we're being asked what happens previously, when we give what happened in the future. But we have a theorem that helps us with those types of problems. So I'd like to look at that theorem. It's called Bayes' theorem. We'll look at it and its proof. Here's a theorem. It's Bayes' theorem. And here's what it says. In terms of notation, in terms of formula, it says the probability of B given A is equal to the probability of A given B times the probability of B all over the probability of A given B times the probability of B plus the probability of A given B complement times the probability of B complement. So this is a fact, and we should prove it. So here, we'll start with the left-hand side, that the probability of B given A is equal to, well, by definition of conditional probability, this is the probability of B intersect A over the probability of A. Now, B intersect A is the same thing as the probability of A intersect B. I'll just write it down that way. Over the probability. Now, A is the same thing as A intersect B union, so that's what A is. A intersect B complement. That might be out of the screen. Let me move that back. So, sorry about that. So the top of our fraction is the probability of B intersect A, which I'll write down as A intersect B, over, and the probability of A, well, that's probability of A is the same thing as I was saying. It's A intersect B union A intersect B complement. Okay, so that's what we have. Is equal to this. All right. One thing I want you to notice is that A intersect B and A intersect B complement, they don't have anything in common. So they're mutually exclusive events. And so we can rewrite that probability. The union of that probability is the sum of probabilities. So, we have the probability of A intersect B over the probability of A intersect B plus the probability of A intersect B complement. And now using our fact that we had before that resulted from conditional probability definition, this is the probability of A given B times the probability of B all over the probability of A given B times the probability of B plus the probability of A given B complement times the probability of B complement. And that's Bayes' theorem. And so we want to do an example where we use this. So let's suppose, here, I'll write some of the example here. Suppose an urn has 8 white balls and 3 red balls. And 2 balls are chosen, one after another, without replacement. The question might be, find the probability that the first is white, given that the second is red. So this is a more difficult problem for us to do. So we use Bayes' theorem, and the reason this is a more difficult conditional probability problem is, like I had said earlier, we're being asked to find out what happened previously, given what happens next, and that's a more difficult situation. And Bayes' theorem allows us to switch that information. So here, this is the same thing by Bayes' theorem. It's probably the second is red, given the first is white, times the probability that the first is white. And then, that's all over. I write down exactly the same thing. Second is red, given first is white, times the probability first is white, plus, and then we write down the probability that the second is red, given, and what we're going to do is write down the opposite, or the complement about the first being white. That is, the first, if it's not white, it had to be red. First is red, and then I have to multiply that, just make it out of the screen, times the probability, I'll write it down here, times the probability that the first is red. Okay, that's what this is being multiplied by. So what is this equal to? Well, the probability that the second is red, given that the first is white. So you know that the first is white, so we imagine ourselves being in that situation. So right now, after the first ball has been chosen and it's white, there are 7 white balls in the urn, and there are 3 red. So this is 3 out of 10 times. What's the probability the first is white? It's 8 out of 11. But the second part is the exact same information. So it's 3 out of 10 times 8 out of 11. Plus, the probability that the second is red, given that the first is red, well, that's going to be 2 out of 10 times the probability that the first is red, that's going to be 3 out of 11. And so those, whatever that number ends up being, is the answer numerically for the problem. So that's an example of Bayes' theorem. And Bayes' theorem can be extended, and we'll do that next. There's an extension for Bayes' theorem. But first, I'm going to need a definition. Okay, so the definition we're going to look at is about mutually exclusive and exhaustive events. The definition. Events E1, E2, you can go up forever, but I'll say they're finite for this definition, but they don't have to be. N are said to be mutually exclusive and exhaustive well, the mutually exclusive part is satisfied by if EI intersect EJ equals to the empty set when I is different than J. And the exhaustive part is that E1 union E2 union, we keep on unioning them all up, and what we get is the sample space. So that's the exhaustiveness. If you union them all up, you get everything. Okay. And so, what I want to list next is something called the total law probability. Some people call it that. This is a theorem. I'll write down the name total law of probability. And here's what I'm going to list. It says if E1, E2 up to En is a sequence, okay, of mutually exclusive and exhaustive collection of events. And A is an event. Then the probability of A is equal to the probability of A intersect E1 plus the probability of A intersect E2 plus the probability of A intersect En. Okay. This can be seen pretty easily with the Venn diagram. Here's what I mean. If this is the sample space, and maybe this is E1 here, and it doesn't have any overlap with E2. Here's E2. Maybe this is E3. And this part right here is E4, and let's say this is E5. So it took 5 events here to be mutually exclusive and exhaustive. And let's say this is A. That kind of oval circle here is A. And someone says, what's the probability of A? Well, the worth of A is this part of A plus 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 this part of A. And that is A intersect E1, the probability of A intersect E2, the probability of A intersect E3, the probability of A intersect E4, the probability of A intersect E5. That's what it is. So, formally, the proof, well, I'll write down is the probability of A is equal to the probability of A intersect E1 union A intersect E2 union all the way up to A intersect En. A intersect En. And because these are mutually exclusive and we're unioning them up by the definition of probability, this is the probability of A intersect E1 plus the probability of A intersect E2 plus all the way up to adding up the probability of A intersecting N. Now, that total law of probability is what's being used in Bayes' theorem in terms of the bottom. And so, let me write down extension of Bayes' theorem. So I'm just going to write down this formula. And here's what we have. If E1, E2 up to En is a collection sequence of mutually exclusive and exhaustive events and A is an event, then I think I have one down here. The probability of A, let me write it this way. Probability of E1 given A, what that's equal to is the probability of A given E1 times the probability of E1 all over the probability of A given E1 times the probability of E1 plus the probability of A given E2 times the probability of E2, and we keep going, adding, until we get the probability of A given En times the probability of En. That's Bayes' theorem. Extended. Okay? And the proof is just like the proof that we had earlier, involves the total law of probability. So I'm not going to give that proof. Instead, I'm just going to do an example, a very simple example, except it's a little long-winded. It takes a little while for me to write it up. Okay, so here's what it says. It says a total of 46% of the voters in a certain city classify themselves as independents, whereas 30% classify themselves as liberal, and 24% classify themselves as conservatives. Okay. In a local election, %35% of independents (62% of liberals and 58% of conservatives voted. Okay. The voters selected at random. The question that we want to do is find. So find. Just enough room to write right here. Find. Well, it has a phrase here. It says, given that the person voted find the probability he, she is independent. Okay. Well, we need to be able to read the problem and gather what information is given to us about probabilities and conditional probabilities. And the first thing that's told is that 46% of the voters are independent. The voters are kind of our sample space, if you will, of the voters of the city. Okay, so here, 46% of the voters are independents. So what that says is the following, if you will. I'm going to be going back and forth for a few seconds. The information that I would get from that is the probability of an independent is 0.46. Okay? Probability of an independent is 0.46. It also said in the problem that 30% are liberal. So the probability of being a liberal is 0.3. And the probability of being conservative, that was 0.24. So that's information that's given to us in the problem. Now I want to go back to the wording of the problem. And in particular, here's what I'm going to say. In a local election, here's what I'm concentrating on. 35% of the independents voted. Okay? So 35% of the independents voted. Okay? What that means is, you'll remember that phrase, 35% of A is B. That translates into the following. It's a conditional probability. What we're being told here is the probability that hold on just a second. 5% independents vote. That given that they were independent, the chances they voted was 0.35. That's what we're being given. Likewise, the rest of the problem says 60% of the liberals voted, so that information is probability that you voted, given that you were liberal, that was 62%, so 0.62, not 69. And then, the probability that you voted, given that you were conservative, that's equal to 0.58. And so what the question is asking us is, what's the probability? So what the problem says is, given that the person voted, so you're given that they voted in the election, okay, what's the chance that they were independent? So that's what's being asked us. And you see the information that I'm being given in terms of conditional probability has the given and what's being asked for switched. So here's what the answer is in terms of Bayes' theorem's extension. This should be equal to the probability of voter given independent times the probability of independent all over the probability of the voter given their independent times the probability that they're independent. Plus, so if we think about the voters, not that they voted, the voters, you've got three classifications of voters. You're either independent, liberal, or conservative. So this is the part about independence. And here I have the second part about having voted given that you are liberal times the probability of being liberal. Plus the probability that you voted given that you are conservative times the probability of being conservative. So that's the extension of Bayes' theorem where we have three events that make up a sequence or a collection of mutually exclusive and exhaustive events. And so here numerically what this is going to be is going to be 0.35 times probability of independence, 0.46, all over, same thing, plus probability that you voted given that you are liberal, that's 0.62, times the chance of being liberal, that's 0.3, plus the probability that you voted given you're conservative, and that is 0.58, times the probability of being conservative, that's 0.24. Okay, so that's the problem now we need to do. The next thing I want to look at, I believe, is that of independence events. So independent events. So what does it mean for two events to be independent? So here's a definition. Two events A and B are said to be independent if the probability of A intersect B is equal to the probability of A times the probability of B. And the idea is that two events are independent if knowing that one of them happened doesn't influence the chance that the other one has happened. That can be seen through a fact in just a second. So here's a fact that I'll list. If the probability of B is greater than 0 and A and B are independent, then the probability of A given B is equal to the probability of A. So here, if you know that B happens and you're asked what's the chance that A happens, well, it's the chance that A happened without knowing whether B happened or didn't happen. Okay? So the fact that B happened doesn't influence the chance of A happening. That's the fact. Let's do a proof of that. here's my proof. We let the probability of B be greater than 0, and suppose events A and B are independent. Then the probability of A given B is equal to the probability, by definition, probability of A intersect B over the probability of B. But since A and B are independent, the probability of A intersect B is the probability of A times the probability of B over the probability of B. And then, of course, the probabilities of B's cancel out. You're just left with the probability of A. So I'd like to look at an example next. Two examples. So, before I get to example, let me say this. As a definition, if events A and B are not independent, they are called dependent events. Now let's look at an example. So in our random experiment, a coin is tossed and a die is rolled. So let A be the event that heads occurred, and B be the event that a 3 occurred. The question is, determine if A and B are independent or not independent events. And really, it should be kind of clear that when you flip a coin and then you toss a die, that whatever happens on the coin toss should not have affected what the die roll was going to end up being. So they should be independent events. But let's check this out using our definition. Okay. So, first of all, very quickly, the sample space in this experiment, it's going to be heads 1, heads 2, heads 3, heads 4, heads 5, heads 6. Or you could have gotten tails 1, tails 2, tails 3, tails 4, tails 5, tails 6. So that's the sample space. And then if we look at the probability of A intersect B, that's equal to the probability that the coin toss was a head. So that's the probability of heads, and that the die roll was a 3. And so if we look at this, and each one of these events in the sample space are equally likely, this is equal to 1 out of 12. Now the probability of A is the probability of getting heads, and that is 1/2, 6 out of 12. The probability of getting a 3 on the die roll, well, that happened twice, so it's twice out of 2 out of 12, which is 1/6. So since the probability of A intersect B equals to the probability of A times the probability of B, that is 1/12 is equal to 1/2 times 1/6. Then A and B are independent events. Okay, let's look at one more example. Excuse me. So let's say, as an example, a die is rolled twice. It says let E sub 1 equal to the sum of the die rolls is 6. And let's let E2 be the event that the first die roll is a 4. And the question is, are E1 and E2 independent? Well, the sample space, very quickly, remember what it is. It's 1, 1, all the way up to 1, 6. And then it's 2, 1, all the way up to 2, 6. 3, 1, all the way up to 3, 6. 4, 1, all the way up to 4, 6. 5, 1, all the way up to 5, 6. And then 6, 1, all the way up to 6, 6. And so the probability of E1 intersect E2, let's look at it for a second. So I'm trying to determine whether these are independent or not. I need to see if the probability of E1 intersect E2 is equal to the probability of E1 times the probability of E2 or not. So the sum of the die roll is 6 and the first die roll is 4. This really means that you're looking for a 4, 2. And so that happens 1 out of 36 times. Now the probability of E1 is that the sum is a 6. So if I look at my sample space over here, and I say, how many ways are there the sum is a 6? Well, in this row, there's 1 way, 1, 5. Here, 2, 4, 3, 3, 4, 2, 5, 1. No way to get a sum of these 6 here. So it's 5 out of 36. Okay? The probability of E2, which is that the first die roll is a 4, well, that's 6 out of 36, or 1/6. And note, 1 out of 36 does not equal to 5 out of 36 times 1/6. Okay? These aren't the same. They're close to being the same, but they're not the same. And so these events are dependent. Okay, dependent. That is that the probability of E1 intersect E2 does not equal to the probability of E1 times the probability of E2. Okay, that's enough information for this lecture. Thank you very much.